the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is another video in the series for my linear algebra students, or for you if you're a linear algebra student, who's going through the matrix equation process right now. And so far you've learned what a matrix equation is. You've learned some theorems about the existence of solutions to matrix equations, that type of thing. We're going to use that theory to do an example here. And actually, if you're watching the videos in the order that I'm intending them to be posted in, even though this one is kind of out of order, you should have just recently watched the following. I took the time to investigate if a solution could be found for this matrix equation right here, where A is, well, this guy right here, and B is this guy right there. And in the process, we made a little note here that it's the same as asking if B is in the span of the two column vectors of A itself. And we found out that there is indeed a solution to this matrix equation. We found it to be, I think it was like 1, -1, or -1, 1. I couldn't remember which right now because I don't have the solution in front of me. But now we're asking kind of a bigger question. What if instead we had, well, the same old matrix A that we had in the previous example, but instead on the right-hand side, the vector B was arbitrary. And we're asking, can a solution be found to the matrix equation AX equals B when A is, well, again, that matrix 1, 1, -3, 8, 2, -1, but B is arbitrary, B1, B2, B3. And if you're watching, again, these videos in the order with which I produce them, then you might guess that we are going to use this theorem right here, that matrix equation AX equals B will have a solution as long as B is a linear combination of the columns of the matrix A. So just reiterating that theorem, if AX equals B, the matrix equation, has a solution, well then the vector B is a linear combination of the columns of A that you see up there to the left. Now, the trick to this, and it's not really a trick, but the thing to note when you're working on a problem like this, is that B is arbitrary. That's critically important here. What they're really intending to ask here is, given an arbitrary vector B, can we always find a solution? They're not saying it that way, but that is exactly what they intend for you to answer. Does this vector equation, which is derived from this matrix equation, have a solution for any value of B? Well, let's find out. We know that the solution to the matrix equation is the same as the solution to the vector equation, is the same as the solution to the system of linear equations associated with this vector equation or the matrix equation, whichever you prefer. Let me go ahead and write out the system of linear equations associated with this. All I did here was go ahead and use scalar vector multiplication and then vector addition to arrive at these expressions that I wrote on the left-hand side of these equal signs here. And then the vector B is actually just B sub 1, B sub 2, B sub 3, so I went ahead and put those in their corresponding rows. This gives us a linear system, and we know that we can place this linear system in an augmented matrix and use row reduction techniques to try to find a solution to the corresponding linear equation. So let's go ahead and place this in an augmented matrix. And just as a reminder, because every once in a while it's nice to sneak in language that we've learned in the past, this matrix, actually the two column vectors there, form what we call the coefficient matrix of that augmented matrix. So, and the right-hand side there, I always call it the augmented column of the matrix. So you might want to use that language as well. You don't have to. I'm going to use row reduction techniques. At this point, you're an expert, so I don't need to actually take my time. We get down to this point right here, and you notice that we have a pivot in the first column, and we'll have a pivot in the second column. Now, depending on how you want to solve this or continue with your row reduction, that pivot might not actually be in that pivot position. It's just a heads up. But At least we know the first two columns have pivots. Now, we have a theorem from way back in the day that tells us if we have a pivot in the rightmost column, then this linear system that's associated with this augmented matrix will be inconsistent. So I do not want a pivot in this final column. That would be a big bad no-no. Let's go ahead and continue doing a row reduction technique here. And rather than using the -3 as my pivot, I'll use the 11 as my pivot, and I'll use it to kill off the -3 below, just to showcase that you do have choice when it comes to choosing which row contains your pivot. So here I'm going to go ahead and do the mathematics. That last little bit of green ink there, that's just me saying, okay, I'm taking 3/11 times this entry, and I'm adding it to the entry right here. I just used green to show that addition, and now I'll clean that up in one final step so that we have all terms, like terms, combined. And technically, I could, in that bottom equation, or that bottom row, I suppose, multiply the entire row by 11, just because it would look a little bit better. So I hope you don't mind. I'm going to multiply that bottom row by 11 to make it look better. All right, so we get down to this point. Now remember, for a linear system that is related to an augmented matrix to have a solution, or in other words, to be consistent, the rightmost column cannot be a pivot column. And so therefore, we do not want this piece right here to be a pivot. We must have that entry be 0 for this system to be consistent. Going back to the original question to make sure we answer it correctly, investigate if a solution can be found for this matrix equation. So it turns out a solution can be found as long as we have that condition right there. Now, how can we visualize that result? That's usually, a lot of students will get to that point and say, okay, I guess that just means that, whatever B1 and B2 are and B3 are, they have to satisfy this equation for this original matrix equation to have a solution. And that is true technically. However, how do you visualize what this means? Well, first of all, this equation, the solutions to this equation, represent a plane, an infinitely long piece of paper, I guess you could say, in R cubed. But not only that, it's a plane in R cubed that goes through the origin, because if you allow B1, B2, and B3 to identically be 0, it makes this equation true. So this is a plane in R cubed going through the origin. And since that plane represents all the vectors B, such that we would have a solution, it has to represent the span of the column vectors of A. In other words, to generate B, remember we have a theorem that says if AX equals B, then B is a linear combination of the column vectors of A. And since we're looking at a plane in R cubed that represents any possible vector B that allows for a solution, then that plane in R cubed must be the span of the column vectors of A itself. Remember, all linear combinations of the column vectors of A will generate any version of the output that we can create. But the only realistic versions of these outputs are the versions of the outputs that satisfy this equation down here, which is a plane. That is, the span of those two vectors, those two column vectors of A, must be represented by that plane in R cubed. Otherwise, this matrix equation is not consistent. It's not consistent for all other choices of B that do not land on that plane. Now, I've told you in the past, I am atrocious when it comes to graphing in 3 dimensions, but I'm going to give this a good old college try. The first column of our matrix A is 1, -3, 2. Going over 1 in the x sub 1 direction, backwards 3 in the x sub 2 direction and up 2 in the x sub 3 direction, we get that green vector that represents the column vector a sub 1. The column vector a sub 2, which is 1 over 1 in the x sub 1 direction over 8 units in the x sub 2 direction and down 1 unit in the x sub 3 direction, is represented by that vector, that blue vector there. And the infinitely long sheet of paper, which represents all possible linear combinations of those two column vectors of A, is represented by the following. Wish me luck as I try this. There we go. That's actually not too terrible for me. That's an infinitely, you kind of have to turn your head to see it, but that's an infinitely long sheet of paper in R cubed. It goes through the origin right there, and it actually goes it goes in all directions, right? So it goes this way as well, whatnot. It still, is on a plane, but it goes behind the screen. So that blue highlighted region and it going on forever in that plane represents all linear combinations of the two column vectors of the matrix A, and therefore all possible values of the right hand side vector B to our equation right here that would result in a solution to the system. Now remember, these vector B's are not the solutions to the system. They are the only vectors B that will allow us to have solutions to this matrix equation. And I said system a moment ago, but I really should have said matrix equation. Anyhow, so that is a full investigation into whether or not we can actually find a solution to a matrix equation when the vector B on the right hand side is arbitrary. Now, if you're slightly confused, if you think, wait, I'm having a hard time wrapping my head around that, why would we have limited outputs for the right-hand side? Let me give you just an algebraic version of this that I think will help out. Let's pretend as though, just like the coefficient matrix A was a constant, actually, it's just a bunch of constants. Let's pretend as though we have a simple equation from algebra where our coefficient is constant as well. We don't know the value of x. And in fact, I wrapped it within the square root for a very specific reason here. Let's just not worry about that for right now. And we also don't know what the output or the right-hand side is. That's exactly what's happening here. We don't know what the vector x is, and somebody's saying, you know what, I don't know what b is yet, but one day I'll tell you. And in fact, it might help you if I just wrote b here instead, just to kind of convince you. Now the question is, what are the possible values of b for which this could possibly have a solution? Not what is the solution, but what are the possible values for b? And in this case, there's an infinite number of values of b for which this does not have a solution. For an example, b cannot be -1 because that would not give a real solution. The square root of something can't be negative. And right now we have 3 times the square root of something equaling b. If b is negative, we've got an issue. So that should imply to us that our choices for the right-hand side here, the scalar on the right-hand side, those are going to be limited. They're limited by the structure of x itself. Technically, they're limited by the structure of the equation itself. And with matrix equations, it's not as simple as just saying, oh, we have a square root. It's much more complex because you're dealing with vectors, specifically the column vectors of A, and the space or the sheet of paper, if you will, or the plane or the line or whatever they're generating, but some space that they're generating, B had better be in that space. Basically, what I'm saying is B should be in the range of A times X. If B has no possibility of being in the range of A times X, then we throw that value of B out of our list of possible right-hand sides. The only right-hand side possibilities are the ones that are in the range of A times X. That's a very hard range to visualize because as you deal with larger and larger matrices, you go beyond simple planes or lines, and instead you get into 3-dimensional, 4-dimensional spaces and so on and so forth. So right now a geometric interpretation is doable, but in the long run it's not very doable because you will not be able to draw them all the time. So instead you really need to start thinking about that good old domain and range idea. It's not exactly like that, but it's a good way to think about it when you're dealing with the matrix equation and you have an unknown right-hand side. You could say, well, I know whatever a times x is, it has a set of outputs, and that set of outputs is the span of the columns of A. So whatever I put on the right-hand side better be within the span of A, of the columns of A. Anyhow, I hope that video was interesting. This is actually one of the more challenging topics within this section of material for students because of the geometry of it. But like I said, in the long run, you're going to let go of that geometry and you're going to hold on to the concept of the span of the column vectors and making sure that that right-hand side is generated, or a linear combination of the columns of the matrix A. Okay, that's it for me. You guys have a wonderful day. I hope to see you in future videos. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.